Okay, so now our second speaker, I'll just have to bring them up on the stage if they're around. Let's see. Hello. Hello. Great. So we have our second speaker, Dr. Hortense Leferrand. Thank you for joining us. Now, I just have to quickly find, all right, great. So with this session, our next speaker, I have a quick bio that I'd like to introduce them with. So Dr. Leferrand is assistant professor at the School of Mechanical and Aerospace Engineering and School of Materials Science and Engineering at Nanyang Technological University in Singapore. She's also a PI at the Singapore Centre for 3D Printing and the Singapore ETH Centre. She earned her diploma, a diploma from ESPCI Paris, France in 2012, a Master of Science in Materials from ETH Zurich, Switzerland in 2013, and a PhD degree with the ETH medal in Materials Science from ETH Zurich in 2017. After a research visit at Purdue University in the USA in 2017, she moved to NTU in Singapore at the Center for Biomimetic Sensor Science under a fellowship from which the Swiss National Science Foundation. In January 2019, she joined the faculty at NTU as an assistant professor. Her research interests are multidisciplinary, essentially focused on developing 3D printing processes, microstructured materials, ceramics, and composites with high mechanical or functional properties. Her work has been recognized by several awards and fellowships, among which the Postdoctoral Publication Prize from the Materials Research Society in the USA in 2018, the Materials and Processes Award from ETH Zurich in 2018, and in 2020, she was awarded the National Research Foundation Fellowship from Singapore, a $3 million individual research grant for early career scientists. And she has lots of fun doing research and developing new technologies. So I found that was just incredible. And I know it's not a panel session, but I'd really like to ask you a quick question about the individual research grant that you got. That's worth $3 million. That is just incredible. Yes. Oh, I can't hear you. Sorry. I'm not sure if there's. Oh, I think we may need assistance.
Is it working?
Oh, it's working now. Yes, yes,
it's working. Okay.
Yeah.
Yeah. So thank you for the introduction. This so National Research Foundation Fellowship. It's similar to the Career Awards in the US or the ERC grants in starting grants in Europe. For Australia, I don't know. There is probably something equivalent. And this is a project that we have to conduct for 5 years. And this is in complement to your position as a faculty. So it really allows you to focus on research and to grow. It's a competitive grant, but it's exciting if you can secure such a grant to have fun with research.
Yes, of course. I'm actually not sure what the equivalent would be in Australia, but I'm assuming the ARC DECRA fellowship, perhaps, or an early career fellowship offered by them would be similar. So, anyway, I'm thoroughly excited for your presentation, and I'd just like to get back into it. Your 3D printing, so the presentation that you will be giving us today is on 3D printing of multifunctional materials with bio-inspired microstructures. And I'd like to ask you to please share your screen.
Yes, of course. Allow. Is working now?
Yes, it's working. I'll leave you to it. Thank you.
Okay, thank you very much. I'm very delighted to speak today in this TIPE 3D conference. And I'm lucky, thank you, Jamin, as well, for giving the previous talk, which was also very fascinating. And therefore, to introduce Singapore and NTU, since the previous speaker was from there as well. So so this work has been conducted in NTU Singapore, and I am in the School of Mechanical and Aerospace Engineering, but also Material Science and Engineering. So the two comes together, but I will try to have the talk not too technical, but more focus on the objectives of the work. So what I really want to share with you is to 3D print small centimeter-sized devices, functional devices. And there are two keys to do this. The first one is to use bio-inspired microstructure to boost the performance and to create unusual properties. So again, in the previous talk, we talked about bio-inspiration by using cells to create some structure. Here, the bio-inspiration is slightly different, is that we are looking at how materials are built, and then we take the key principles and then try to translate these key principles into artificial synthetic materials. So here I should show two examples of these structures. The first one is a bilayer microstructure that we typically find in pine cones or in edamame seed pods. And when you take a pine cone or edamame seed pod, if you dry them, they will change shape. And the reason there is this change in shape is because they have an internal microstructure that is a bilayer with different orientations of cellulose fibers. So for the pine cone, we can schematize this structure into a 090 layup. And for the edamame, it would be a +45 layup. So when you dry this kind of structure, you observe bending. And this is already applied in synthetic materials. Common and exciting example of this natural microstructure is what we call nacre-like structure. Nacre is this very colorful layer that you find in seashells. If you take the seashell, break it, take it under the electron microscope, this is what you would see. It's a very ordered structure with mineral bricks that are assembled and aligned in a brick and mortar fashion. This is also quite established that with such a microstructure, you can give at the same time strength and toughness, which usually are two properties you cannot really combine in a material. And for maybe 20 years, maybe more, people have been trying to reproduce this kind of structure in ceramics to make tough ceramics, so like unbreakable ceramics. And so current results are these black dots here. So these would be some nacre-like ceramics. And if you compare with the other metals, are overlapping with these nacre-like ceramics in these strands and toughness plots. So it's very exciting to mimic these microstructures to generate new properties and enhance the performance. So bio-inspired materials, they are useful in many engineering applications. So here I take a review paper I really like that they published in 2018, where they show various applications of these nacre-inspired materials for nanogenerators, gas barrier materials, fire retardant materials, electrical cables, supercapacitors, and structural materials. So these are examples of applications. But I like to pose the question, can we increase their complexity? So nacre-like is like a wall with a brick and mortar structure, but can we make it even more complex? Can we make more functionality? And can we make these kind of materials ready to be produced in a larger number? And so this comes the second key point of this vision I want to share with you, which is that we can use 3D printing to combine the high performance and the multiple functions. So imagine in the future, we want a very small portable smart device. So we could imagine 3D printing already directly the different components next to each other or on top of each other or entangled within each other, like a supercapacitor. There could be a battery, thermoelectric materials, sensing functions, and so on. So this is more detailed in this paper we wrote in the Journal of Materials Chemistry A last year. So to sum up, so the way we want to make these small centimeter-sized devices is by using bio-inspired microstructure and 3D printing. So how are we going to create these bio-inspired microstructures? Throughout this talk, I will talk about magnetic fields from magnets as the tool we use to create this bio-inspired microstructure. So we use a magnetic field, an external magnetic field. And more specifically, what we use is a rotating magnetic field. So this picture that you see, the square, like the rectangle in the middle, that would be the material. The red would be particles that have some properties, and the green would be a matrix. And they are assembled, as you can see here, in a very well-ordered structure, a little bit like the nacre, but in another direction, like a vertical nacre. And this was done using a rotating magnetic field, which is symbolized with these circles. Okay, so rotating magnetic fields is what we're going to use to build these microstructures. So how does it work? So now I share with you a little bit more details. So this is a method that was developed not by me, but by someone else in 2018, 12, sorry, so 10 years ago. And the principle is fairly simple. You take a small microplatelets, for example, typically 10 micrometer in the diameter. So here the example is aluminum oxide microplatelets. You put them in water and you add iron oxide nanoparticles, and then you make sure it's the opposite side, electron charge, so that they would absorb electrostatically at the surface. Okay, so you make this new microplatelet that is responsive to magnetic field. Then you have these new particles, you place them in water or in some kind of a liquid. So here are the picture of these platelets that have been modified, and then there is a background liquid. And then you place a magnet, for example, here, and you rotate it along this axis. So I'm trying to share a video here. Wait a second. Arrow. So when you rotate the magnet at a small frequency, the platelet, they will turn. And when you increase the frequency, at some point, you see they start to align perpendicular to this axis. And you see they align parallel to each other, a little bit like in this nacre-like structure. So rotating magnetic fields at a frequency higher than 3 Hertz for particles suspended in the liquid, that's our method. Now this is in liquid, so if we want to make a composite or a ceramic with this, we need to start with a suspension, align it, and at the same time to remove the water. So this is what we do. But to do this, we need to design our suspension, which is here, in a smart way, which I will explain now. So in this graph here, we have horizontal is the volume fraction of these modified platelets in the suspension. In this, we have the viscosity. This is the free volume of the platelets to move. And this is the alignment angle. And we want to align the platelets vertically because vertically it's the most challenging. So if we can do, then we can do any orientation. So what these graphs show is that if you have low volume fraction, the platelet, they have a lot of free space to move around, but you cannot really align it as you want because of the forces such as the gravity or any hydrodynamic flow that will put the platelets down. If in turn you are too concentrated, there is very little possibility for the particles to rotate and to align themselves. And at the end of the day, you cannot align. So there is an optimum window of concentration in this to make the suspension to allow this orientation to be retained, especially after drying the material. And you can see now this in the SCM images. If it's too dilute, it's kind of random. If it's too concentrated, it's also kind of random. But there is a sweet spot around 20-25 volume percent where we can really align the platelets nicely, and then you can dry it and it will stay aligned in the very nice direction. This concentration, that depends of course on the platelets that are used. These are aluminum oxide platelets of a certain size. If you change the size, change the platelets, it will change, the window will change. Okay, so now we have our microstructures aligned. So how do we turn it into a composite and a ceramic? So either you use it as such without post-processing and you get a material. So here we did that using boron nitride platelets to make high thermal conductive materials for electronics. You can also infiltrate it, and then you can make strong and tough polymer composites. So here we varied the orientation and showed that, well, the nickel-like is indeed the toughest. Or you can bring it into a furnace, sinter it, and transform it into a ceramic. So these samples here, they were sintered at high temperature, but also hot press. So you apply pressure at the same time as the temperature. And this leads to ceramic that are very difficult to break. So this is what we call this tough nickel-like ceramics. And we can make even more complex microstructure if we modify the orientation of the magnet as the sample is dried. So basically, as long as the sample is a little bit wet and as long as the platelets have space to move, they will be able to align with your magnetic field. Once it is dried or once it's too concentrated, then they will get stuck in their orientation. So this is what we applied to create this kind of 0-90 periodic orientations or to smoothly vary the tilting of the platelets. And yeah, so this is one last sample by one of my staff, Xin Ying. She made this beautiful structure, which really looks like a seashell, where we have multiple orientations and it changes within the plane. So this is nice. So we have a tool to make microstructure, but now you're going to tell me how to make an object out of these materials. And that's where 3D printing comes in, of course. So I want to introduce you, I have a bit of time, two methods that we recently developed where we can 3D print these materials. And these are slightly different methods that are also complementary. The first one is called magnetic drop and demand that was developed by my former postdoc, Liu Wing Chen. And the work, you can find it in Nature Communications, and it's also patented. So if you're interested to co-develop a product with this, please reach out. And the second method I will show afterwards, is continuous magnetic directing writing, which was developed by my postdoc Lid Sikwan here, also published in Additive Manufacturing, and this we are also patenting. So also if there is interest, please reach out. So how do this printing works? Magnetic drop on demand, it's a simple method. As the name indicates, we deposit drop. So it's not inkjet as in the previous talk, it's really deposit a drop onto a substrate. This drop contains these magnetically responsive platelets that I showed just before. We deposit the drop and then it's a nice shape like this, like on this image as well. At the same time, we apply our magnetic field and we align the platelets. This is fairly low concentration, between 5 and 15 volume percent. But when we do this, the particles they actually sediment nicely to reach a higher concentration up to 20-50 volume percent. So it increases the concentration, it sediments, and then the water of the ink dries out, and you're left with a horizontal surface, and inside you have aligned platelets. So that's one drop, and then you repeat it. So it's a voxel by voxel printing. And for each voxel, you can change the composition, you can change the orientation as illustrated in this cartoon. And each of these kind of voxel is about 100 micrometer in the thickness, and the diameter varies a little bit, more or less around 1 millimeter. And you can create small objects as in this picture. So here are some SEM images to show the control. This is a vertical structure where we varied the angle, made with an ink containing the same aluminum oxide platelets as I showed in the part on the microstructuring. So you can see we can really tune the angle as we desire. And we can do it vertically, but although we have to take into account that there are some deformations at the interfaces. Now, I was talking about devices and properties. So how is that actually interesting? So that's where applying these to different materials is also interesting. So I'm going to take you through these graphs. The first one here, we use graphite platelets, same process, and then we tune the tilt of these graphite platelets into these printed droplets. And we measured the anisotropy between the direction Rx and the direction Ry. So when all the graphite are horizontal, there is no anisotropy. But when you increase the angle, you increase the anisotropy in electrical conductivity so that you can make functional devices that have high conductivity in one specific direction. In this other example, we use boron nitride platelets. And here, what we looked at was the cooling of a material depending on the orientation of the platelets. And so we found that this was also varying depending on the orientation of these platelets. Here, it's also with the alumina platelets, and we also varied the angle of these platelets, and you can see we can really tune the mechanical properties. So this is the stiffness and the Vickers hardness, so that we can tune by controlling this angle. If we create multiple angled structures, like this vertical kind of thing, we can also combine or generate new properties. For example, multi-layers in orange will have mechanical properties that are in between the horizontal and the vertical. And so typically we get something that is a lot stiffer, but also a lot tougher than if you have only one orientation. And the last multi-material property control I want to show is we can also combine different materials together to build functional devices like a capacitor. So this is graphite, aluminum oxide graphite, and we also measured that if you vary the orientation of the middle layer, you would vary the capacitance of this capacitor. So as an example of smart device that we can build with this, I show here a self-cooling mechanical sensor with tailored sensitivity. So this is how it looks macroscopically. So you can print several together at the same time by depositing all these drops. And the design was to have a graphite pillar with vertical or with control orientation and do this on a slightly larger boron nitride surface, so that the boron nitride will do the cooling when the sensor is working, because you need to have an electric field throughout the sample to measure the deformation. And so it's a mechanical sensor. So what we do is we apply pressure on it, and then you measure a variation in the resistance. And the design comes handy because when you control the angles of the graphite in this sensor, so I'm coming to this plot here, you can tune the sensitivity of this sensor. If you have only vertical, it's not going to be very sensitive, but you can apply high pressure. If it's only horizontal, it's linear only at the beginning, and then you cannot apply very high pressure because then it's not linear. But if you have mixed orientations inside this pillar, you can extend the range where it's linear towards higher pressures. And this is quite useful for making a sensor that it has a controllable response. And at the same time, we can cool it during operation thanks to the boron nitride, so that we don't risk any overheating or short circuits because of the heat problem. So that's one example that we can do with this method. I'm sure there are many. So the advantage of this magnetic drop on demand is that it's multi-material, it's high precision, you have a high quality of the microstructure. One problem, however, is that it's a bit time consuming, because if you remember, we need to wait for these platelets to sediment and to dry. So this motivated this second technique, which is continuous magnetic directing writing. So here the principle is to make an ink that we extrude directly, and while we extrude it, we align the platelets that are inside this ink, and at the same time we print on a slightly porous substrate that will dry and fix the microplatelets in their orientation. So here we had to optimize one thing, is the time to align the platelets should be shorter than the time for printing, because this guy is going to move forward, right? And the time for drying. So we need to control to make sure we have these kind of relations. And to do this, we developed optimized ink that contains magnetically responsive microplatelets, so the same as before, but we added fumed silica as a rheological modifier to make the printable ink. So here I already directly show you some of the microstructure we can get. So you can basically orient the platelet as you want within one 3D printed filament. You can make, of course, multiple filaments, but unique capability is the orientation within one filament, as illustrated here. And so what kind of material can we print with this? I will show you two examples. The first one is with ink containing aluminum oxide platelets, where we can make strong and magnetic ceramics. So we print and then we sinter at a high temperature. We can make small objects, as you can appreciate on this image. We can make porous objects also as well. These objects are usually magnetic because we have to add a lot of iron oxide in our ink. So they will stick to a magnet, and the mechanical properties are anisotropic and are fairly reasonable for a ceramic. So yeah, rather high strength and high flexural. The second application is using the same method, but instead of using an alumina, we use graphite. And here we can make strong magnetic and electrically conductive materials with the same quality of microstructure control, as you can appreciate here, of shapes. The materials are also magnetic, but they are also electrically conductive after a reduction at 1050 degrees. So what kind of device can we make with this? So we can think of different applications. Here we illustrated it by making a kind of electrical cable that you can remotely uh, uh, remove or orient using a magnetic field, like a remote controllable switch. So in short, our 3D printing methods allow us to locally design objects to boost their performance and combine functionalities. Future work, like the question is like, which design should we use? How to design this microstructure, how to design this complex material. So for this, stay tuned. We are still, of course, developing these methods. So this is my last slide, where I would like to acknowledge my team that you can see here. That was this summer where we were still in COVID. If you want more information on the research, you can find more on this webpage. You can follow on Twitter. And so here are the people who have been doing these experiments. So I'd like to thank them. I'd like to thank again the Research Foundation for the funding at Nanyang Technical University. And I would like to thank you for your attention. And I'm happy if you have any question now, or you can also email me at this email address on top of the screen. So thank you very much. I stop sharing.
Sure. Thank you. Thank you, Hortense. That was really fascinating. Just the depth of research that you have done is I admire it. So thank you for sharing that with us. There was lots of questions, I think, in the Q&A chat, but I'd like to take advantage of my power as moderator, and I'd like to ask my question first, if that's all right. So early on in your presentation, you showed us a little graph, and it showed the optimum window for the suspension concentration of the platelets. And I just wanted to know how that's correlated to the particle size, the platelet size distribution, and how that size impacts the window and the work that you're trying to do.
Yeah, that's a very, very good question. We have not formalized this because there are several factors. It's all down to the viscosity of the suspension. And viscosity depends on particle size, but it also depends on the particle interactions, on the particle aspect ratios. So rheology is a very complex field, actually. So we have not looked into this, but what we have done to simplify the system was to take these aluminum oxide platelets and simply just vary the size. So if you take aluminum oxide platelets, same surface charge, but use smaller size, the viscosity will be much higher because a smaller size would lead to higher viscosity. So you would shift this window towards lower concentrations. If the particle size would be bigger, it would be towards much higher concentration. And then, so actually you vary this window, and then it will also influence the final property that you get at the end. Because if you have smaller particles, you would use less, but they would also pack better. So it's a multifactorial kind of system.
Interesting. Lots to consider there. That's awesome. Well, I'll ask you the first question that's been upvoted. For the no post-processing boron nitride sample, do the platelets just stay together without a matrix or sintering? And they refer to slide.
Yes, no, that's a good question. I think I forgot to mention one thing is that in the suspension, we have platelets, we have a solvent, typically I use water, but we add a little bit of polymer, like 5% of polymer inside. And so when you dry, this polymer is kind of a binding everything together. And so it's just dried polymer. If you put it back in water, it will dissolve. But if you use it in a dry environment or in a natural environment, it will maintain the structure integrity.
Okay, good to know. And so the next question up here is, what sort of imaging was used for the video on slide 11? I don't recall what slide 11 was, but
that was
hopefully...
where the platelets were rotating. That was just an optical microscope. That's it. Maybe it's because the particles were shiny, but this is because the particles, they had some kind of a coating that make them reflect light and some interference, but it's just optical microscope with the camera.
Okay. Was that the colorful image?
Yes.
Yes, the colorful. Yeah, I remember that one. That was very cool. And so the next question, what sort of applications can use the different cooling properties based on orientation angle of the particles?
Yeah, so for this, we are looking for applications in electronics, especially the high power electronics, where you have 3D stacks of power chips. So we are used to have a PCB board with one chip onto each other. That's what our current electronics is. But people are now developing, instead of having a PCB board, to have like a compact block of chips that are very close to each other. So if one or several heats up, then it would heat the thing altogether. So in this case, what we think is with these platelets, we can, and we proved it in the paper actually, we can direct the heat towards certain directions according to the platelets orientation. So let's say we can make a material and direct the heat, for example, towards the side where there is no chip. So that's this kind of application. So high power electronics.
Interesting. High-powered electronics. And so we've got our last question, which is, how long does it take for the platelets to sediment and dry?
Sediment and dry. Okay, so that's the drop and demand method. Let me look at my notes. So for one droplet, I mean, depends on how big it is, but generally it's takes like 10 minutes. So you can imagine to make a device, if you have to wait 10 minutes for each droplet, it takes some time. So we calculated that to make the pressure sensor, actually the pressure sensor took 45 minutes to make, but it's still too long. So we have made a few tests where we modify the ink by adding more volatile solvent so that it's a little bit faster, and we can also add some temperature to make it a little bit faster.
Okay.
But there is still time needed, yeah.
Okay, fair enough. Well, I hope that you're able to help speed up the process and achieve the amazing results you're achieving right now. So thank you for your time and your presentation. Yeah, I'll just give you a round of applause. And if I could ask you to please turn your mic and camera off, and I will ask the next presenter to please turn their camera and mic on.
Okay, yeah, thank you very much.
No worries,
Bye.
thank you.